And this is, as I mentioned, the second installment of this series. Today we're going to focus on managing water. And this morning, my name's Bowden Fisher. I'm a Water Quality Extension Associate with Ohio State University Extension, and I will be your host this morning. We also have Bruce Clevenger, Associate Professor with Ohio State Extension and Defiance County A&R Educator. Also, we have Bridget Moneymaker, who is also a Water Quality Associate with Extension, and they will be helping moderate today. So if you have questions, feel free to send them a chat. Our first speaker is Dr. Aaron Wilson with Ohio State University. He's an atmospheric research scientist at the Ohio State University, and he holds a joint appointment with the Byrd Polar and Climate Research Center and OSU Extension. He's also with the State Climate Office of Ohio. So welcome, Aaron, and we look forward to having you this morning.
Thank you so much, Bowden, and thanks to everyone for being here this morning. It's certainly an honor to be talking about weather once again. I sort of see myself in today's program as sort of a provocateur. I don't think it's hard to kind of provoke conversations when we think about changing weather patterns and climate. But certainly what I want to do is just set the stage a little bit from the weather side and then get out of the way and let the other speakers really get to the heart of the matter here, which is how do we respond? What can we do with these, how do we manage water really, as the title says, in today's wet and dry growing seasons? So that's really what I want to get to today. So, just kind of a context. Just kind of a context here, starting very locally. Starting out when 2020. Give me just a second. I'm sorry. Sorry for the interruption here for just a second. All right. So, just to set the context, the local context here, we're looking at just the area in 2020, what happened last season. Very warm conditions across Ohio, Indiana, Michigan as well. In Ohio specifically, this was the 7th warmest year on record, going back 126 years, right? Looking at the region, we see a lot of wet and dry areas. This isn't atypical, right? We see a lot of regional, spatial heterogeneity across our region here. We had drought conditions from the Dakotas down through Iowa. We also had very dry conditions from Missouri up into northwestern Ohio here. But most of the state was wet here in Ohio. It was actually the 29th wettest year on record over the last 126 years. So asking Bruce up in Defiance County or others there in Northwest Ohio, didn't feel like a very wet season. And just kind of putting 2020 in a broader context, and if you've seen my talks, I try to look at these things from a little bit longer perspective as well. If we rank the 126-year record, both in terms of temperature and precipitation, 8 of the top 10 warmest and 8 of the top 10 wettest seasons in Ohio have occurred since 1990, right? 1990. So in the last 30 years, 8 of the top 10 warmest and wettest years have occurred, looking at the entire record over 126 years. So we've got some whoppers in there, right? Recent whoppers, 2017, 2018, 2019, all in the top 10. But we've also had some quite dry years, 2006, 2012, within that record as well. So let's talk a little bit about that relationship. And to do that, I want to zoom out a little bit and think of it from a more global perspective. 2020 is now ranked as the 2nd warmest on record, going back to 1880 for the globe. It's only behind 2016 by 0.04 degrees Fahrenheit. Okay. 2019 is the third warmest on record. So 10 of our top 10 warmest years have all occurred since 2005 for the globe. And you can see last year the spatial differences compared to the long-term mean in our mid and low latitudes, tropical regions and mid-latitudes here, where a lot of the globe was much warmer than the 20th century mean. So if you were born after 1985, February of 1985, you've never experienced a cooler than average month for the planet relative to the 20th century mean. So we know that we're getting warmer, but specifically when it comes to water, why does that matter? How does the atmosphere warm and why does it matter? Okay, so we've got greenhouse gases, CO2 and evaporated water being the large contingent of that. evaporated water, they become warmer as they absorb infrared radiation from Earth's surface. They don't care about the shortwave radiation, the high frequency visible light coming from the sun. They're interested in the infrared radiation, the long wave radiation that comes off the surface. Those molecules absorb that, and it keeps our atmosphere habitable, about 60 degrees Fahrenheit warmer than it would be if we did not have the CO2 and the water vapor in the atmosphere. Water vapor, though, is the most dominant greenhouse gas. It's not the most powerful. It is the most dominant greenhouse gas, and it's a fully function of temperature. Okay, so that temperature comes into play primarily through evaporation. Okay, so the evaporation rate, the rate at which we evaporate water from the surface and put it into water vapor into the atmosphere, depends on the temperature of the ocean and the air as well. Okay, so we can imagine if we fixed our temperature, we kept our temperature constant. If we added more water vapor, it would immediately condense and fall out as precipitation. In order to build that capacity for the water vapor, the temperature has to go up. Okay, the temperature is warmer, right? And so we need to make sure that we know it's the warming of the temperature that's driving the water vapor changes. Okay, so that extra water, it's in the atmosphere, it falls out as precipitation within a week or two, but that CO2 remains for a long time. So there's a feedback here. Okay, CO2 added to the atmosphere as a greenhouse gas, it warms the atmosphere. The warming atmosphere increases the evaporation, which then further warms the air. Okay, so CO2 has an amplified effect on that water cycle. And that's essentially what we're talking about when we're thinking about managing these wet and dry seasons. Water vapor is not a forcing of climate change, but it's a feedback of the climate change. So we can imagine our water cycle, a lot of complex components here, but from evaporation to condensation to precipitation, okay? We know that as our evaporation rates increase, it leads to greater amounts of water vapor in the atmosphere. It leads to more potential in our precipitation as well. And we've got a pretty simple equation to equate these two. For every 1 degree Celsius we rise in temperature, we increase our water vapor about 6 to 7.5%. Okay, a standard what we call the Clausius-Clapeyron equation for our atmosphere. Okay, so again, this increased evaporation not only leads to more water vapor in the atmosphere and heavier downpours, these extreme events, but what about in the middle of the growing season when we're hot, we're evaporating quite efficiently from our surface here, can lead to intense drying periods. So warmer conditions leading to faster evaporation rates, and we're evaporating that water off the surface. So we can have abnormally wet seasons and very intense dry periods embedded within those wet seasons. And that's exactly what we've been dealing with. So kind of put it a little bit in perspective here, looking at just over the last 30 years since 1990. These are the seasonal average temperature trends for winter, spring, summer, and fall on the left. Okay, so definitely there's some seasonal differences across our region when it comes to our average temperatures. We know that winter, a lot, we've seen warming in the winter, especially if we go back farther and we compare it to the middle part of the 20th century or even earlier. But over the last 30 years, that rate of increase has been, you see a lot of gray shadings here within a half a degree per decade. We see a lot more warming locally in the springtime, summertime as we get close to those Great Lakes, because the Great Lakes are also warming and they don't have as much of a cooling effect on the surrounding areas. And then even into fall, when we see large areas of the country with really strong fall warming trends. Looking a little bit closer into our region, again, spring and fall, these bigger trends, but also in summer and less so in winter locally. We've got some temperature trends for overnight lows, for instance, in our fall season, upward of 4.5 degrees over the last 30 years. Okay, so these are the temperature changes that are then driving some of the evaporation changes that we're seeing. Now, if we look at our seasonal precipitation trends over the last 30 years, right, pretty much they're a wet signal for much of the Great Lakes and the Ohio Valley region. There are some regional differences and there are seasonal differences that are really important to pick out here. So generally, we're looking at wetter than average conditions, But you can look at some particular months, for instance, July and August, and you start to see trends that are a little bit opposite to the seasonal trends, where it might be rainy and pretty wet in June. July, we start seeing some flat to negative trends in precip over the last 30 years across the state. Again, the warmer conditions driving those evaporation rates. And once you set that evaporation in motion, once that water vapor is evaporated from the surface, right, over this larger area, then it limits those daytime thunderstorms during the summer as well. And we always hear the terms or the phrase drought begets drought. Okay, this is how that gets established. But this is how we have these intense drying periods embedded within abnormally wet seasons. So a 29th wettest year for the state of Ohio, but what happened even this past summer? And we'll get to that in a moment. Some of the work that I've been looking at is looking at some of the extremes within our global climate models, and then using those to see how our extremes might change in the future. One of the observations that we've made, since 1980, just looking at 1980 to 2018, and there are numerous studies that show this and reflect this, just the change in annual precipitation. So we know that increases in precipitation across much of the domain and leading to wet soils, erosion, things like that. But, just looking at some of these trends, for instance, in Louisville, Kentucky, right, over the span of 1980 to 2018. So we're looking down in this region on the map, we're talking 3 inches per decade increases in our precipitation per year. And we see that across a large area of Ohio, Indiana, much of lower Michigan as well, right? And just think about 2012. Okay, this was 2012. I've got 2012 marked at the peak, the bottom peak here on the right. That precipitation was, greater than a lot of the annual precipitation totals in the 1980s. Okay, so it's just kind of a perspective. The drought of 2012 having more annual precip that year than much of the 1980s. Again, looking at the extremes a little bit. Again, how are we getting that annual rainfall? A lot of it's coming in those heavier downpours, right? We've got these local changes, these blue areas denoting where heavier precipitation events are increasing in magnitude. A number of studies looking at this as well. And I'll put a plug in for something a little bit more local, looking at the effects of rainfall patterns over the Western Lake Erie Basin here with this Williams and King paper. For those that want to do, a little bit more reading on some of the local impacts, I would encourage this resource as well. But we still see drought, right? So all of these increases in extreme precipitation and annual precipitation, but we still see drought. So we're really, looking at this. Again, this is 2020. We had 38% of the state of Ohio covered in moderate drought conditions in a year where we were the 29th wettest on record. Okay. Again, what is happening to our summer and our fall conditions? Again, these droughts, these intense drought periods due to warmer temperatures and increased evaporation rates, right? So this immediately calls into question, how do we manage these water resources when we have some extreme variability, year to year extreme variability, and within the season as well? And that's really, I think, our challenge today. And when we look in the future, we see a lot of our precip changes driven by increased water vapor and seasonal changes to our atmospheric circulation, to where we see these wetter, cool seasons, the fall, the spring, the winter time, and drier summer seasons, intensified drought, perhaps water shortages that we have to deal with a lot more often, even though it's likely we're going to be in a wetter environment, okay, overall, if we look from a longer perspective. So kind of my thoughts for today and for the program really is to think about the global versus the local context. Impact and responses depend on where you live and what you're doing and your operations and all of those things. And I think that you're going to get a lot of insights from the three speakers today. It is a world of extremes now, right? We can take one of our warmest Marches and one of our coldest Aprils. Well, climatologically, that's an average spring, right? But we know that we're seeing this high variability. So how do we deal with these rapid shifts between our hydrologic reality, our hydrologic extremes? And I think we should be thinking about, how do we respond, both individually and collectively? How do we look at our landscapes? How do we look at our individual fields and our operations as part of this landscape to respond and to adapt? I always say I have the easy job. I just get to talk about weather a lot. I think the hard discussions and the hard things are really in managing that. And so hopefully you'll pull those insights from today's program. It's been an honor as always, and certainly looking forward to any questions you might have at the end of the program. Thanks. I'll turn it back over to Bowden.
Thank you, Aaron. We really appreciate you coming on today. Appreciate that content in of itself, and also for setting the stage for the rest of the program. So thank you very much. And we will continue onward with our next speaker. So I'd like to introduce Dr. Eileen Kladivko. She's a professor of agronomy at Purdue University, where she teaches and does research and extension work in soil conservation and management. Her research focus has been to identify soil management systems that improve environmental quality and promote agricultural sustainability. Specific research areas have included impacts of tile drainage on crop yields and nitrate losses to surface waters, the interactions of earthworms, soil management, and soil physical properties, as well as cover crops and conservation tillage for soil health improvement. So we're excited to have Dr. Kladivko on with us today, and that I will hand it over to you. Thank you.
All right, thank you, Bowden. Can you see my slide?
Yes, we can.
All right, very good. Well, thank you, everybody. I'm glad to be visiting with you virtually today about drainage, which is one part of what Aaron kind of led us up to. We got a lot of times where we have a lot of excess water, and drainage is one of the ways that we deal with that. So I'm going to share some information and learning that we've had from a long-term drainage research project in southern Indiana that certainly has implications way beyond southern Indiana. So this is a kind of picture that we don't want to see in our crop fields, of course, and these naturally poorly drained soils, and we have plenty of them in Ohio and Indiana and around the Midwest, give us a lot of challenges for crop production, even in a normal year, let alone a wet year. And so subsurface drainage, or tile drainage, it's often called, is certainly a common water management practice that we have for crop production throughout the Midwest. And I'll just remind you that these tiles are often seasonal in function. They're not flowing all year long. In much of Ohio and Indiana, they're flowing late in the fall and on and off in the winter. They might not be flowing today in most of our places, but and then all spring, but they quit usually in midsummer because the water is being used by our crops instead. So what I am going to share today are some results from a 35-year project. I've been lucky enough to have been involved in one of the few kinds of long-term projects that we've been able to do. And it's a project at SEPAC, Southeast Purdue Agricultural Center, down in Jennings County in southeastern Indiana. But as I mentioned, what we learned from that is much more applicable, much more broadly in our drained agricultural lands throughout the Midwest. The original goals of the SEPAC studies were to look not only at drainage, but to look at improving the soil. So this was a Claremont silt loam soil, so very similar to soils in southwestern Ohio also. A very poorly structured, low organic matter soil that's high in silt and naturally poorly drained. The impeding layer is a fragipan that's down at about 3.5 to 4 feet deep. And our goals were, first of all, to improve drainage. Secondly, to improve soil physical properties. That soil has a lot of erosion problems, and so we wanted to reduce crusting and erosion. We wanted to increase infiltration and permeability. And obviously, we wanted to improve crop growth and yield. And this study was initiated because farmers in that part of the state had been asking Purdue to look at the modern perforated plastic drain tube or tile drains that really came into heavy use in the 70s, but had not yet been used on that kind of a soil. So the goals of this study, which started just right after I arrived at Purdue, were these. The SEPAC drainage research site had drain tiles installed at 4 different spacings. My ag engineering senior colleague, Ed Monk, wanted to look at what was the optimum drain spacing. And so the drains were installed at 5, 10, 20, and 40 meters, or 16, 33, 66, and 132 feet apart. The 40 meter or 132 foot was considered to be the undrained control. On this particular soil, since water moves so slowly through the soil itself, Ed Monk and Jerry Mannering and Ron Wheaton, the three senior researchers on this, said that essentially the soil, anything that was growing in the middle of that 132 foot spacing was basically not going to feel the effect of drainage at all. So that was our control, our undrained control. The tiles were installed at 2.5 to 3 foot depth to stay above the fragipan layer at 3.5 to 4 feet deep. And we used standard 4-inch plastic drain tube and no sock or filter, but it was installed at a pretty good grade, a steeper grade than in many other places. It was at a 0.4% grade to keep any silt that might get into the tile flushed out. The tiles were installed in February and March of 1983, an unusually dry and warm February and March. And they were installed with the standard equipment of the time, with laser guidance and with a trencher machine. And I just showed you the main drain along the highway there, and then the laterals went up into the field. The laterals then exited into this metal culvert because we wanted to be able to monitor drain flow and to sample waters. And then once the water was sampled, then it went out from this culvert into the main drain into the ditch. So what I'm going to really cut right to is the results of 35 years. And the first one is that drainage pays. And I'm sure that many of you breathe a sigh of relief, but of course you already knew that. But what I hope to add today is a little bit more discussion of some of the different ways that drainage pays. First of all, drainage improves the timeliness of field work. During our first 10 years of this 35-year study, we tilled and planted the individual drain spacings when each of them were ready. So we did spring chiseling, which was the common practice at the time in the 80s for that soil. We did spring chisel. We would go out, the farm superintendent and I would go out and we'd look at the soil. And if the narrow spacing was ready to chisel, he would chisel it. And the next day there would be a secondary tillage and planting. If the other spacings weren't ready, then we would repeat the process the next day. Okay, maybe now the 10 meter is ready to chisel and plant. And of course you can imagine what happens is that in some years, you might have a progression of this drain spacing is ready. The next day, this drain spacing is ready. And then the next day it rains, right? And so it sets the ones back that didn't yet get tilled and planted. So for the undrained control plots, over the course of those first 10 years, they were delayed compared to the narrow spacing, anywhere between just 1 day in a warm, dry year and 15 days in a year where we had several rainstorm events in between the chiseling of the first plot and being able to chisel the undrained control. So obviously, more timely access to the field is a major benefit to most farming operations, and certainly even more of a benefit than in our 15-acre field when farmers have bigger fields and more of them to deal with. This is just an illustration showing you some evidence of the soil drying or drainage. The light color here is that the soil has dried or drained. And the farm superintendent just superimposed, drew on there the drain lines where they were. So this light colored soil is all in the intensively drained area. And then the dark colored soil, which is still very wet, is in the middle of this undrained control, okay? So you can see very clearly that the drains were in fact effective on the soil that they weren't sure they were gonna work. They did work, they did drain the soil faster, and the undrained control certainly stayed wetter for longer. Okay, what kind of yields did we get? I'm going to show you some some examples. I'm going to show you the first 10 years, and then I'm going to show you some of the later, more recent yields, and then kind of an average over everything. So for the first 10 years, as I said, we chiseled and planted when each spacing was ready, okay? On average, if you look at the bars on the right here, the 10-year average shows that the narrowest drain spacing, the dark blue here, had the highest yield, and then yields declined as the spacing got wider and wider. And our undrained control, the light blue on the right, was 10 bushels per acre less on average than was the narrowest drain spacing. And frankly, that was kind of disappointing that it was only 10 bushels difference, and we were surprised. We were expecting greater differences, and later on we did get them, so stay with me here. But on average, the first 10 years, there was only a 10 bushel yield difference. And that's in part because there were only 2 years that were really wet out of that first 10 years. Most of the years were average or dry. But you can see that in some years we had the effect that we kind of expected. The narrowest spacing had the highest yield, and they kind of stair step down, right? So 89 and 92, for example, very clear. Other years, the middle two spacings had the highest yield. In 7 of the 10 years, the undrained control had the lowest yield, okay? So pretty consistently, the undrained control did not do as well as the drained treatments. Okay, so that's the first 10 years when we were doing chisel tillage. Let's take a look at moisture first, then we'll move on to some later yields. The other thing, of course, that's of interest is besides the timeliness, we could get in earlier, besides the greater yield with the narrower spacing, we also had a moisture at harvest benefit. We did harvest them all on the same day, and you can see a 2-point moisture difference. The narrow spacing had about a 21% grain moisture content on average over the 10 years, whereas the undrained control was up 2%, up at 23%. So obviously, this is also a benefit to a farmer if the grain is drier when you harvest it, then you have less drying costs. All right, let's look at some of the later yields. So these are corn yields from 2007 to 2017, which was the last year of corn in this particular experiment. And after the first 10 years, we switched to a corn soybean rotation, or sometimes a corn soybean rotation. So we did not have corn every year. These are the corn years during that 11-year period. And you can see that there are some years where the 3 drain spacings, like in 2007, the 3 drain spacings are pretty similar and the undrained control is down just a little. And the same thing in 2011 here. But most of these years, you see a huge difference from where the undrained control is, like 50 bushels lower for the undrained control or more, compared to the other 3 drain spacings. And the other 3 drain spacings were often quite similar to each other, but the undrained control was much, much lower, reflecting the fact that during this time period, we did happen to have quite a few wetter years than what we had in the earlier time period. So obviously drainage pays a lot more when you've got wetter years. I want to talk about another aspect of timeliness that you may not think about first off as being a timeliness issue, but after the first 10 years, starting in 1994, we switched to no-till. So all the plots were planted on the same day. We didn't have that difference in when they may have gotten planted and how that might have affected yields. Because we had switched to no-till, we didn't have to wait any longer for the top 6 to 8 inches to be suitable for tillage. We really just had to wait until the top 1 to 2 inches were suitable for planting. So we kind of picked an intermediate date when they were all ready. So they were all planted on the same day. So we did not have a timeliness benefit for drainage compared to the undrained control. But of course, if the season continued to be wet after planting, in extremes, you may need replanting, which is kind of another aspect of timeliness. So for example, in 2017, All of the plots were planted on May 16th, but the undrained control didn't make it. And so it got replanted on June 2nd. And then this picture is taken on June 12th. And we're centered here, this area that looks very almost bare, but you can see the corn rows going off into the distance here. That's our undrained control, and that's the growth from the replanting of June 2nd. Whereas you can see on either side of that, we've got corn that's off and running. That was from the original planting. We basically didn't have anything left from the original planting, and this is the replanting. So this is another way you could think about timeliness, right? Well, maybe you got planted, but it got drowned out and you had to replant. And so drainage here is really affecting our timeliness from that standpoint. Okay, so let's pull that all together. Drainage pays our bottom line here. Drainage improves crop yields. These are the corn yields averaged over the entire years of corn in this 35-year experiment. There was about 24 years of corn. The undrained control averaged 144 bushels per acre. All of the drain treatments were in the 160s. And if you go here to this narrowest drain spacing, 168. So a 24 bushel per acre yield benefit averaged over all of the corn yields. So this obviously becomes much more significant as far as a financial gain when you've got that kind of a yield increase over the course of this long-term period. We did not, for whatever reason, we did not actually see a benefit of drainage to soybean yields, and maybe in part because we typically plant soybeans quite a bit later. But if you look at the average over here from 1994 to 2018 during the soybean years, we had no significant difference among all the spacings, including the undrained control. I've shown you some of those yields here, some of the later years, where you can see very little difference. You can see in 2018, the undrained control was much lower than the 3 drainage treatments. But in 2016 and in 2014, for example, the undrained control was a little higher than the drain treatments. So on average, over all of the soybean years, which was 10 or 11 of them, we basically saw no difference in soybean yields due to drainage treatment. Okay, what about surface drainage? The farmers in that area remind me periodically that my particular field has pretty good surface drainage compared to the fields where they have Claremonts, which are on much broader, bigger flats than where ours is. So we've got slightly more slope. It's still less than 1%, but slightly more slope than some of the other Claremont fields. And so you would anticipate that the importance of subsurface drainage would not be as dramatic on my field if it's got pretty good surface drainage compared to more typical fields that don't have good surface drainage. So I'll show you just one illustration of that where you can see the impact of having tiles versus not having tiles on another part of that larger field that had less than ideal surface drainage. So in the foreground, you can see essentially nothing, right? The untiled, that was an untiled portion of the field, and it was planted 3 times and was drowned out 3 times that particular year, which happened to be the year after that part of the experimental field. We stopped the experiment and they were just bulk farming it, okay? That kind of happens, but so planted 3 times, drowned out 3 times because the surface drainage was inadequate and water would stay ponded on the field for too long for the corn to survive. In the background behind that line that I drew is the tiled portion of that field. And you can see the corn stubble, and the corn grew just fine because the ponding didn't stay there because the tiles were able to essentially remove that ponding. So again, for fields that are larger, that don't have perfect surface drainage, tiles have the benefit of removing those potentially ponded areas and removing those potentially drowned out areas of your field and eliminating those. Okay, let's look at a different aspect of drainage paying. In this case, drainage is improving the performance of other conservation practices. So in this case, I'm showing you cover crop growth. On that spacing field, going back to the spacing field, in later years, we started growing cover crops in some years. And if you're going to grow a cover crop, right, if you're going to start doing any kind of conservation practice that's related to improving soil health, or maybe taking up nitrate so it doesn't leach into the tile drains, which is part of what we were trying to do with this, and it was very successful. But you can see here in the upper left, this was in 2016 in the middle of May. This was the tiled plots, and you can see pretty good cereal rye growth. And when we cut that, we got about 3,100 pounds of above ground biomass per acre in that cover crop growth the day before we were going to spray it, terminate it so that we could plant soybeans. On the lower right, you can see the untiled plot, and you can see we had a reasonable stand, but the growth was very small, very, very poor, very slow. We had less than a fourth of the biomass that we had where we had good drainage. So again, if you're going to go to the trouble to plant cover crops for whatever your reason is, nitrate scavenging or soil health building or whatever it is, you want the cover crop to grow. In this case, because we were going into soybeans and because it was a wet year, we had a lot of growth. We don't, up here on the tiled, we don't always let the cover crop get that big. If we're going to corn, we try to kill it sooner. And if it's not a real wet year, we usually get planted earlier and we don't kill it so late. But we always get better growth where we have drainage than where we don't have drainage. And just the magnitude of that depends on the weather in a given year. And it also depends on which crop we're going to be planting and how big we want to let it get. So again, drainage is going to improve cover crop growth if you're growing cover crops. And then that pays. I'm going to switch gears a bit again and talk about another experiment that I don't talk about nearly as much. I mostly talk about those 4 drain spacings, and we've done that. I want to talk now about this other experiment where we were looking at subsurface tile drainage versus none, and that's the one I showed you the picture of. Okay, that ended right before that year where we didn't get any growth at all. So in there we had, besides drainage versus no drainage, we had chisel versus no-till splits on the plots. And then we had 5 agronomic practices that we designed for the purpose of improving those soil physical properties that I mentioned earlier. So continuous corn, CC in this case is continuous corn, not cover crop. That was our control treatment, just corn. Then we had one treatment that had a winter cover crop of either wheat or cereal rye, another one that had a winter cover crop of annual ryegrass, another that had manure applications in the spring, dry animal manure. And then the last one had a 3-year rotation of corn, wheat, and then an orchard grass, red clover meadow. And we hand broadcast the covers into these plots. They were 100-foot long plots, but that was what we were doing at the time that we did this experiment in the 80s. What did we find in a nutshell? A couple things. So the blue bars here are tiled and the red are untiled. So the percentages that I have listed here are the percent increase in corn yield averaged over the 9 years of that experiment for the tiled compared to the untiled. So for continuous corn, there was a 12% increase from tiling compared to untiled. For all the other conservation practices, there was about a 20% increase in yield for tiling compared to the untiled. Okay, so those practices made a difference in the tiled. The other way to look at it is to say, look across all the treatments. So the blue bars here, the tiled, when you compared it to just continuous corn, these conservation practices were either equal or greater in yield than just continuous corn, all right? So the conservation practices were beneficial. However, where you were untiled, the conservation practices were less or equal than the continuous corn. So in other words, the conservation practices didn't really do you any good and may have hurt in those very wet plots, those untiled plots. On occasion, I did some other measurements like counting earthworm populations or measuring soil physical properties. So earthworm populations in general were higher where we had no-till versus chisel. And we have this from many studies that I've been involved with, and many others have found that. Generally, earthworm populations were higher where you had tiled plots versus untiled. Generally, they were higher where you had covers and rotations of manure compared to the control. And soil physical properties, we measured a few of them, primarily aggregate stability and infiltration. And they tended to be improved by cover crops and rotation, especially where you had drainage. So what I take out of all of that is that drainage pays. It enables other conservation practices to work better. So if you have a naturally poorly drained soil, then when you try to implement conservation practices like no-till or cover crops or rotations with hay crops, it's going to be more effective both in increasing your crop yields and in improving your soil physical properties, or soil health would be what we would call it today, in the tiled field versus the untiled field. So adequate drainage is really a necessary first step to improving both crop yields and soil health if you are in a naturally poorly drained soil. Okay, so tile drains are a long-term investment. Drain flow develops over time in the soil. The yield effects, of course, vary from year to year. Conservation practices take time to improve soil health as well. But the long-term improvement in the cash crop yields and the cover crop growth and the effectiveness of the other conservation practices make tile drainage a good investment. So my last slide is just if you want more details, I have some extension publications that are brand new, as well as video presentations of those that go into a little more detail than what I just told you. You can watch parts 1, 2, and 3, where I talk about the yields and the timeliness, the cover crops, and then the drain flow and nitrate loads I didn't talk about at all today. And those are on my Purdue drainage website. And extension publications on the same topics can be found either at the Purdue Education Store or the drainage website. So with that, I think I'm just about a minute over, but I'm done. Thank you very much.
I'd like to introduce Dr. Larry Brown as our next presenter. Dr. Brown is a professor of agricultural engineering at The Ohio State University and state extension specialist in agricultural drainage. He's going to share with us some years of research in subsurface drainage as well, and also some about sub-irrigation. So welcome, Dr. Larry Brown.
There's my contact information, and if you want to follow, anybody wants to follow up with me after this presentation, I'd be happy to visit with you. Okay, just to do a brief introduction of some terminology, what we are calling since the 70s, the total package or system of drainage is called water table management. And with that, we have the conditional subsurface drainage that you are aware of and knowledgeable about. And we have controlled drainage, which in today's time we call drainage water management. And then sub-irrigation. Somebody's got the video turned off. Should that be turned on? Okay, thank you. Okay, I should put Indiana on here too, but Eileen's study is the longest term drainage study that's been conducted that I know of in North America. And then we have two 20 to 25 year studies that have been conducted in Northwest Ohio. Eileen's study is a very, very good study, and it's good to see the results after so many years. So let's see. The Professor Schwab started work in Ohio in about 1955. And the first thing he did was set up a long-term drainage study, looking at undrained, surface drained, subsurface drained, and combination drainage on roughly 100 by 200 foot plots, I believe. And these are the results. Of a number of years of that study. And so the yield advantage based on the drainage practice is the second line of data, and those are the yields. You can see that back in those days, we were really busting it. Okay, now, so did a real simple, Dr. Schwab had a really simple economic analysis done, and I'll explain a little bit about that in a few minutes. Just to illustrate these, this is for corn, and you've got these bars are the yields, and what you have in the background here is the percent yield variability. And what you should see here is that you've got, as you increase the drainage effectiveness or intensity, you end up decreasing the year-to-year variability in these yields. And that shows up quite often in a lot of the studies on the clay soils that we have in Northwest Ohio. And so he studied and looked at corn, oat, and soybean. And here, I don't know why this keeps flipping back, but anyway, it's very important to manage the drainage on these poorly drained soils in Northwest Ohio. And when we do that, and we do it effectively, we can reduce the year-to-year variability. Okay, Dr. Schwab did a little bit of economic analysis, and basically what we see here is that if we put, for every dollar we put in to subsurface drainage on corn, surface drainage rather, we get $3.50 back. Soybean, $2.10 back. So as you look at these based on a dollar input, and this is what you would get back in terms of surface drain, subsurface drainage, and then the combination drainage. And these are from North Central Ohio. Now, when I first came to OSU, we got started working on some plots that Don Eckert had at Northwest Branch, and this again is the Hoytville Silty clay. The soils that Dr. Schwab worked with were Toledo clay. And so the bottom was the first 14, or I think 12 to 14 years. And before we made some changes, I apologize, there's something going on here. And then we ran the study through 2009, and there was a period of time after 1995 that we ended up creating a lot more treatments to look at rotation, look at ridge tillage, plow, no-till, strip till, and zone builder. So you've got the raw data, or the data here. I'm going to illustrate some of this in just a few minutes. Okay, on the first 12 years of the study, looking at continuous corn, rotation corn, and soybean, rotation soybean, we can see what the range and yields are over that period of time. And this would be the advantage rather. And this 17 was basically when we started doing a little bit of no-till later in the first 12 years. So these are the yield advantage. And what I'll kind of note here, and I'll show this in some other data we have, and when you've got rotation in corn, you end up having a small yield boost. And I think Eileen showed that a little bit of that on some of her data. Okay, so the benefit to cost ratios, again, for every dollar you put in, you get $1.70 out to $2 on the continuous corn, and so forth. Okay. Okay, and I think that's self-explanatory there. So there is a benefit over time. Now, in looking at the longer-term study where we had all the different treatments, the rotation, ridge till, and the different tillage systems, consistently we see a 24 to 39% increase in corn yields compared to the the undrained or surface drained only plots. And this was done in Wood County, Ohio. Okay, so it's a nice trend there. Soybeans, the yield increases had a little bit wider spread, but 13 to 46%. And again, every year we showed higher yields with soybean than we did with the surface drained only crop. Again, notice in the rotation versus continuous, not much difference here. Let's go back to corn just a minute. But when you got rotation versus continuous in any of these tillage systems, we have a little higher yield with the rotation than we do with the continuous plots. Okay, and then this was just strictly on the rotation for the corn, and nice trend. And this is really supports why we should be doing rotation, crop rotation. And there will be looks like there will, at least on this soil, there will be a drainage advantage by doing that. But 11 to 23% over the period of time that we did this comparison study. Okay. I've already mentioned what the soybean and corn and soybean yield advantages are. And again, to note that what we have with the rotation, what that helps us with in terms of increasing the yield, and that was over all of the tillage practices. And we rarely, on those plots over those years, we rarely saw an advantage due to tillage. And so we always have people ask, what about the tillage system? And we didn't really see much of an advantage due to tillage system. Some years, no-till. Once we started the no-till plots, we had a little bit of an advantage there. Okay, let's talk about drainage water management. And basically, we used to call this controlled drainage years ago. And we've got drainage water management practices all over the Midwest now. And got a long-term project started years ago, and that work continues. I think Northwest Ohio, due to the work of the Ohio Department of Agriculture, has put in somewhere between 300 and 400 control structures in the Northwest Ohio area. So it's popular, particularly when there's cost share. Okay. From 2008 to 2014, we had a number of field sites in Northwest Ohio. And at each site, we had a free drainage. If you look at the illustration on the left, a free drainage zone, and then we had a drainage water management zone. And so we had an outlet separated, and we knew what the drain spacing was. And we collected yield off of those for several years and did a yield comparison. So the yield difference we had with controlled drainage, this means that we are trying to conserve some of the drainage water, and they were not free drainage in the drainage water management zone, but we had free drainage, which we didn't impact or didn't control at all on the free drainage zone. And there were studies similar to this and all across the Midwest. And so we look at about a 6% or 10 bushel per acre increase with corn over the period. And then with soybeans, about 3.5% or roughly a bushel and a half. So we don't have the yield response that we had when we go from undrained to subsurface drained plots. But there's a little bit of a yield advantage. Some years there was not a yield advantage. Kind of just depended on the distribution of rainfall. Okay. Ohio Department of Agriculture, as they were putting in a number of these control structures over the past several years, they conducted a survey with the farmers, and these are some of the results that they ended up discovering. Over 50% of the farmers had a noticeable increase in both corn and soybean yields. 0% saw a noticeable decrease in corn yield, but only 4% saw a noticeable decrease in soybean yield. And I think that was consistent with some of our results that we had earlier. Okay. Now, Dr. Jane Frankenberger at Purdue and Eileen Kadivko at Purdue, they have a team of people across the Midwest that have been looking at a number of sites where we had controlled drainage. And this study got started, thinking about 6 or 7 years ago. And so we had ended up having 55 site years of data with corn, and that was under controlled drainage. You can see what some of the results are. Again, not very large yields, but still some yields. And then at some of the sites, we had only less than 4% yield increase. So again, consistent with some of what we've illustrated before on some of our earlier plots and earlier fields. There will be some papers coming out by Dr. Strock and Dr. Helmers sometime in this year. And those will be, I'm assuming those will be available to you if you're interested in gaining a copy of those. Okay, now let's go to sub-irrigation. We can do controlled drainage on most sites where we have conventional subsurface drainage. Controlled drainage works better when we've got a very flat or nearly flat landscapes. With sub-irrigation, it's much, much more important that we have flat zones where we can add the water and be able to provide a constant water table depth to irrigate the crops. So this is really critical. So you go from conventional drainage with minimal technical challenges, then you go to controlled drainage. And for the effectiveness of controlled drainage, you have to have flatter landscapes, but it does work on some sloping fields, particularly if you have a flatter zone at the foot of the field. And when you go to sub-irrigation, you need to have relatively flat zones, and where you have less than a foot of elevation change within the zone so that you can maintain a water table level consistent with the land slope. And that would be on corn and soybeans. We have a number of studies in Ohio where we've been doing drainage sub-irrigation compared to drainage studies. One of the ones that we have in Northwest Ohio is in Fulton County. And although I think we've got 12 or 13 years of data, what I had was where we did sub-irrigation. Part of the time we do during the growing season, but we have controlled drainage during part of the season. Before and after, 53 bushel per acre advantage when we had sub-irrigation, and this is a Hoytville silty clay soil. For soybeans, much smaller yield advantage, but 9 bushels per acre, and that's over the 10 years of the study. The illustration here shows you where we have the irrigation and drainage zones, and then we were harvesting water everywhere within the yellow stripes, and that water was then sent to a wetland, constructed wetland. We're cleaning it up a little bit, and then that water could either go right back up into the field or could go into the reservoir. And we can pull water to and from the reservoir to use for our sub-irrigation work in this field. So this was a really nice study, and learned quite a bit about harvesting drainage water and reuse of that drainage water. Yields from this particular site, these are not all the yields, but what I want to show you, consistently, sub-irrigation yields are greater, and except in 1 year, and that's when we had excess rainfall. And so we didn't have any yield difference during that period, that particular year. You look at, and that's for corn. When you come back and you look at soybean, our yield differences are just not as dramatic and as large as they are with corn. And again, notice in 2003, again, we actually had a little bit better yield where we didn't do sub-irrigation. Okay, and that sometimes worked out that way. So there's your yield. We had a 4-year study down in Pike County in southern Ohio, silt loam soils this time, and we implemented this type of a water management plan with sub-irrigation being 80 to 100 days, and usually starting about the middle of June, late June, and with raising the water table. And you can see some of the data. Oh, come on now. Okay, and our yields. I'm really impressed with the yields that Eileen got on that Claremont soil in Indiana. We don't get that in with our Hoytville plots, our Hoytville soil very often. But you can see what the yields were, and with sub-irrigation, with corn, with soybean, and with corn, we had in these years we had a yield increase every year, a yield advantage. In 1997, well, I take that back. In 1997 with corn, we had a little bit larger yield with the non-irrigated, and in 1997, our yield advantage of soybean was less. And so what we found out was that in 1995 and 1998, we had a partial season of sub-irrigation. And you still see what kind of yield advantages we had with both corn and beans in those 2 years. And then full season of sub-irrigation in 96 and 97. And then something, you had to really kind of watch the rainfall, but we had a little over 7, almost 8 inches of precip during the sub-irrigation period in 1996. In 1997, we had almost, not quite, twice the amount of precip during the sub-irrigation period. And so with soybeans, that effect is seen here. And with corn, that's when we had the increase with free drainage, and that had a little bit to do with not lowering the water table to release some of that sub-irrigation water when we did have rainfall events. So learning a little bit from these studies. Okay, I want to make just a comment or two. Sub-irrigation on some soils, particularly flatter landscapes, it will, you can get yield advantage. There are a number of farmers, several farmers that have been doing sub-irrigation in Northwest and North Central Ohio for many years and have done quite well, and they continue to do that practice. But what makes it really pay for itself, helps pay for itself, is having a cheap water supply. So if you've got very high pumping costs, that's going to decrease your profitability. So water is critical. The water accessibility is critical. If you're pulling out of a pond or pulling out of a lake or a ditch, you don't have to worry about cleaning the water up before you use it. Put it back into the field like you would if you were working with some sort of irrigation system. So some advantages there compared to other irrigation methods. I know Dr. Bud Belcher was at Michigan State many years ago, had done some analysis looking at the differences between using overhead irrigation and using sub-irrigation. And overall, there was not that much of an advantage by going to either subsurface drainage or sub-irrigation or overhead irrigation. But I think he had 1 or 2 years of study where he looked at that. Want to advise you and look at how the Utility Protection Service, or if you're from another state, you have Utility Protection Service. If you call 811, that'll get you to, in your state, that'll get you to your Utility Protection Service that services your state. So before you dig, give them a call. There's my contact information. Want to make a note that Dr. Norman Fauci was involved with every one of these studies. And he was with the Soil Drainage Research Unit of USDA ARS. Also, Barry Allred led the project up in Fulton County with the Shenniger site. Bruce Clevenger was also was involved with the site that we have in Defiance County, and wanted to make note of those people. I'm going to be retiring, and I've got some people who will continue to work with the drainage school, and they will be sending out some notices later this spring about a possible late spring or early summer program that'll be virtual. And Dr. Vinayak Shedeker will be taking over some of the responsibilities for the drainage school and working with several engineers within RCS, ODA, and others to be able to continue running the program. Feel free to contact me if I can help you with anything I've shown you here today. And I guess that's it. Thank you for allowing me to ramble through this.
About irrigation. And so I'd like to introduce Mr. Lyndon Kelly. He's served as irrigation educator for Michigan State University and Purdue Extension for the past 11 years, working in the areas of irrigation management and water policy. He's provided irrigation design and management education to producers and industries relying on the 1.2 million acres of irrigated land shared by Michigan and Indiana. With 35 years of commercial corn, soybean, seed corn, and vegetable irrigation experience, Lyndon has learned to look for the increased yield and reduced risks irrigation can provide without endangering natural resources. So we appreciate you being here, Lyndon, and look forward to what you'll have to share with us. So thank you. There
Is
you
that
go.
better?
That's
Okay.
perfect. Now you're ready.
So my name's Lyndon Kelly. I work a job that splits my time between Purdue Extension and Michigan State University. Out of Purdue Extension, I'm based out of the Ag Engineering Department, and out of Michigan State University out of the Extension Department. We'll talk a little bit more of why that is, but it basically comes down to that the two states share the bulk of their irrigation right along the toll road corridor, mostly to the west of Indiana and on the west side of Michigan. So that's the greatest pool of irrigated ground east of the Mississippi, about 1.2 million acres of irrigation in that area. I grew up in St. Joe County. That's the heaviest, densest area of irrigation east of the Mississippi. And if you drew a circle around Middlebury, Indiana, roughly, you would get, within 2 hours drive, you'd find that 1.2 million acres of irrigation. So I'm here today to talk to you about exploring irrigation. Most of the time I'm working on irrigation design and management, but I get an opportunity to talk to potential irrigators to help them explore whether this is something the road you should go down, or whether this is something you want to stay away from. If you take a look at that pivot that's right there, I want you to notice a couple things. There's cans in the field, so we're doing a uniformity test. Notice the water's coming out the top of the pipe, sprinkled on the top, and the end gun's on at the far right side of the pitcher. We'll talk about that in a few minutes. So as irrigators, what we want to do is we want to supply the water that rainfall doesn't. And this has got to be a little bit of a tricky thing to talk about, because everybody in the climatology area and our weather people are all talking about the wetter environment the Midwest has. And yet we end up using a little bit more water for irrigation to get it done. So it's a little hard to explain. More water, as Aaron had talked earlier, it's a wetter environment, but we need more irrigation to get the job done. Longer periods of time and less predictable amounts of water during the growing season. Here we got a chart that gives us the monthly rainfall totals in the blue line, and the corn need in the red line. Obviously, the corn doesn't need anything in January and February and March, where we are now. And then that field starts using some water. As we warm up, we get a little bit of evaporation. We put the seed in, it starts using water, and that's the red line. At some point, almost every year, there'll be a time period that the need for water will be greater than the rainfall. If we have very good water holding capacities in clay type soils or loam soils, we may be able to meet that need, that red line need, where it is higher than the rainfall, by soil storage, by water storage within the soil. But what irrigators have done is relied on the aquifer that we built up in January, February, March, and again in October, November, December, and pulled that water back up to supply the water when the crop needs it. And if you look at our blue numbers, 20 years ago, I would have told you our average rainfall was 34.6 at the site that this was at. We're now at a 10-year average of 38, so about 4 more inches of water. And yet we went up about an inch in water needs because of that. There are heavier rainfalls, but we don't hold them at this site because of the water holding capacity is smaller than what a lot of our rainfalls are coming to. So what's the interest? Well, the interest in expanding irrigation is this idea of economics. Farmers want to make money. They look at it and they look at where they want to be in the future. And a lot of people are talking about, because of the higher transportation costs, as we, especially now as we're looking at fuel going up in price, a lot of our vegetables and processed vegetables are coming from the West, okay? And so moving that to the Midwest saves a lot of mileage. It's part of the local food discussion also. Can we grow more of our food here locally? The higher input costs that we have with all of our fertilizers and chemistry that we're putting on fields makes it a greater risk to produce produce, vegetables, high dollar crops. And because of that, companies want to reduce risk. So they're looking for environments that have the least amount of risk. And then last but not least, we're in an area where we're increasing the amount of water we're getting, depending on who you're talking to, for the next 40, 50 years. The West is due to run lower in the amount of water, and they've made a consistent decision to feed the populations and not the agricultural resources. So if you were an irrigation specialist in California, you would be talking about how to make the most money out of the least amount of water. And we'd be talking about almonds, and we'd be thinking about almond milk. Here we're talking about corn and soybeans versus vegetable production that was in our area at one time, but is left. That doesn't mean that the irrigation decision is right for you, and there's going to be some discussion about that as we go. So I borrowed a couple slides from the Great Lakes Water Charter. Ohio's part of the Great Lakes Water Charter. It's that agreement that between the states and the federal government that if we manage water in this area, we can say no to diversions. So the federal government cannot take the Great Lakes water and ship it to the West or other areas. But the important things on this map is when you see the areas that prosper in irrigation in northern Indiana and southern Michigan, it's on those green soils in the upper map, very coarse textured sediment soils, okay? And then what matches to that is those soils also have a very high amount of recharge. When rainfall comes, two things can happen. It can either run off the top to a drain, to surface drainage. In your case of your guys' tiled fields, it could be picked up by drainage and then go to rivers, lakes, streams, or drains and remove. Or if we don't have any of those things and we have very coarse textured soils, we just rebuild the aquifer underneath. And so these areas that have these very coarse textured soils also have very high amounts of recharge. And that makes it very sustainable. Most of the area that we're irrigating in Indiana and Michigan, we are getting between 8 and 12 inches of recharge a year, actually more recharge per acre than we pull out for irrigation. So the next thing, if we were going to think about irrigating, would be, is the water quality good enough to be able to put on the field? And we don't, most of us here in the Midwest are blessed with very good water quality, and this is just a minor issue. Up in the Toledo area, we run up into Monroe County, Michigan. We have some salinity issues. We have a little bit of calcium, and we see some deposits that form in like trickle irrigation lines and cause some problems. So those are some quality factors. The 3 bullets at the bottom are 3 excellent papers or sites that you can go to talk about what your water test looks at and how much salt or how much contaminant could a given crop take from that area. A lot of that work's done out of Colorado State, other places where they have much more things floating in the water than we do. Here we think about surface water as being a problem, and as far as quality factors, and it's mostly due to the issue of human consumption foods. If we're looking at non-processing vegetables, we're going to have GAP requirements, generally accepted practices for safe food production, and they will have an E. coli standard. Most of them, for producers, what they're worried about is whether they have E. coli free or low enough testing water the 3 days before harvest, and that becomes a limiting factor. Almost all of our surface water bodies will, by harvest time, late July and August, will have E. coli limits or E. coli positive tests. There's also some diseases in some vegetables that come from can be transferred through the water. And then the other thing we don't commonly think about, but will sneak up and get you, a lot of our lakes treat for Eurasian milfoil and other plant pests, and they use 2,4-D and dicamba-based materials. So if you're spraying those on soybean fields or tomato fields, there's some huge chances for devastation. So how much water do you need? Well, the rough rule of thumb is about 5 gallons per minute per acre that you intend to irrigate at that site. So a 500 gallon a minute pump can provide an inch of water every 4 days on 100 acres. Okay, so that's 5 gallons per minute per acre. And that's going to need to run about 24/7 when you get the hottest part of the summer. Almost every summer, we're going to have about 2 weeks. You're going to run 24/7 with that well to keep up, or you're going to have to start it before you actually need the water to bank some water in your soils, your water holding capacity in the soils and the root zone of the plants you're growing. There's people that split things apart and people that group things. If you look at the chart up there, alfalfa, corn, field beans, soybeans, potatoes, all of them are above 1/4 of an inch a day at their peaks if we're having 85-degree weather, and they're all below 3/10 of an inch a day. So somewhere in that 27 to 32 hundredths. Most of the time with our water holding capacities in our soils, we can get by on 5 gallons a minute. Some of the vegetable companies, when I speak for them, they'll say, Lyndon, drop that 5 gallons out. We'd like to see 7 gallons a minute. We want to be able to have optimum yields in a 2012 style drought, a 2008 or 2012 style drought. So they don't want to depend on those. And oddly enough, you can actually use less water if you have the capacity, because you can wait to put it on until you actually see what the weather brings you. So the next question is, well, is that water actually legally available to me? And Ohio is east of the Mississippi. All the states east of the Mississippi are practicing some form of what we call the riparian doctrine. That's a doctrine, not a law. It is a set of rulings that's been made by your state based on what's right. In Indiana and Michigan, there's court cases back right around the turn of the century, 1908, 1917, those time periods that have helped set the set of what we call doctrine instead of actual laws. The states still have the authority to pass individual laws that modify that, but for most parts, we deal with riparian doctrine. That means the water's there to use as long as you don't negatively impact any other riparians. Both Michigan, Indiana, and Ohio all reserve groundwater rights, like you're floating on a mat above the bathtub and you're just pulling water up through. So they assume we're all coming out of that same aquifer. And so they don't worry about things like pulling water out and not using that water on that land. But they all also observe for surface water purposes, this riparian doctrine, and that's the little graphic at your bottom right. You have to have the title for the land has to have the edge of the lake or stream to legally be able to use that. In the 3 states, Ohio, Michigan, Indiana, that is not a function of government to enforce that. It's one person suing another. It's also one of the few places I've seen irrigators forced to turn the pump off immediately. The sheriff come out, padlock the thing down, or pull the fuses. So it's one of those things you need to know about. If you're using surface water, you are at risk of another riparian claiming that you're a non-riparian user and asking to have you shut off. Not a problem for groundwater. Matter of fact, it's very common for a lot of our cities and municipalities to go out into the country where the water's still fresh and clean underneath the ground and put down a well to bring clean water back into town. So you can transfer property, well water from one location to another. We'll talk about Michigan or Indiana and Ohio rules in a second. But we said, well, as riparians, we can't negatively impact another riparian user. And often that comes up as when your irrigation well outcompetes the home well. So if you look at that purple line, think of that as the top of a funnel. And the irrigation well is at the point where the water would go out the bottom of the funnel. And that zone of influence, that triangular shape or cone-shaped area, is the water flowing in to the well screen or into the groundwater where your pump is pulling it up at the same rate that you're pulling it out. So that zone of influence, if you get into where you're affecting the neighbors and you actually draw them down. So look at the upper graphic there where the red line is. If I actually pull the water down to where their well sucks air and they no longer have the quality or a quantity of water that they had at one time, I may be forced to pay the neighbor's cost at reestablishing the well. Doesn't mean I can't use the water. I've just got to make him whole. And we've seen court cases in all 3 states where that has been in effect. In some cases, you want to try to avoid the best you can, get your well driller on the site and help them figure out what wells may be at risk. Or in some cases, it's cheaper just to right off the beginning, put a new well in that's equal depth as the irrigation well. So in Ohio, on the books, you have a registration requirement. It doesn't say specifically when, but we're assuming that before you use it, you should register it, or at least in the year it was established, it was registered. It looks like it's supposed to be done by the landowner, although some of the well drillers are taking care of it, I understand. It's a responsibility to tell the state where you're pulling that water from. They also have a reporting requirement. Annually, you're supposed to be turning in a report. There's paper copies online at the website given here that basically you're telling them what months you used the water in and how much. So there's a little bit of record keeping there. Nothing that would say you cannot use the water, just that if you're using the water, you have some responsibilities. How are we going to get that water? Well, in most cases in Ohio, it's going to be a deep well. It looks like some of those are going to be rock wells. So here is on the far left is depicted as a well that's pulling out of till. The till wells that are coming out of sand and gravel till, you're using a screen at the bottom. Rock wells, we actually use the rock as our screening material. There are areas, and maybe you're lucky enough to be in an area where there is some shallow groundwater, and we see the 2 center sets of wells as being able to pull those in. The suction wells, we are actually using a centrifugal pump on top, and we're only pulling water from 6 or 8 feet. The important thing here to remember is that the material around that screen has to be coarse enough to let the water come in at the same speed that your pump is taking out. Any type of suction well or shallow well, you're going to use huge amounts of water of energy to vacuum the water out of the soil. You need to have something porous enough to let that in. And then the horizontal wells is a situation that we see that's become more popular here in the last 20 years. It's the idea of using something very comparable to your drain tile with a nylon sock. Sometimes I'll call them sock wells because of that. They'll lay down 60, 100, 200 feet, sometimes going both directions, and then pull a vacuum on that and pull water in. These tend to be fairly low-cost wells in very specific locations. That material in that 200 feet or 100 feet or 200 feet of sock well that you have has to be coarse enough to allow that to happen. We see a lot of these actually placed very close to drainage ditches where the material has been cleaned, and if we have a sandy bottom, they have locations to be able to do that. So there's information on the website at the beginning that gives people that install horizontal wells. Pretty small industry, so it's not a very long list. It looks like Ohio has got a major project going on right now, mapping water availability. They have some very coarse maps up for the whole state, and they're currently have some counties already mapped and have much better county level maps that are worth looking at. I think in the next slide I'll present that. There's areas of the state, if we said, well, we need 500 gallons a minute to get 100 acres irrigated, there's a few areas that you're going to be able to do that from a groundwater resource in that medium blue color. And there's a few areas about in the same geographic location through the center of the state and the upper northwest area that you may be able to get that out of groundwater, but out of rock wells. But notice your rock well's highest level is 100 gallons per minute. So it's pretty slow getting anything out of those rock wells. And that's going to be a major problem to getting fast enough volumes to be able to run overhead irrigation. Some of you are going to be thinking about surface water, and we talked a little bit about where that is. You may want to have a talk with your drain officials that if that is, they consider that's their water or your water. If you've been thinking about how to get rid of it all your life, you never worried about it, now all of a sudden you want it back. Do be concerned about contaminants that are in there, but there's a lot of new projects coming on that are looking at surface water as a recycling system. A lot of places where we can get ponds to come in, but remember that most ponds are good irrigation sources if they refill fast enough. It's not the pond's capacity, it's the ability to refill that pond that really counts. Because of that, we talk about looking at ponds, ditches, and streams in late July, early August to look at whether they're going to be good sources of irrigation. It's bad situation when you make the investment for the equipment and then run out of water right at the peak time of need. Larry brought this up before and some of his subsurface irrigation discussion, this idea of using a reservoir. There's a few places in Michigan, central Indiana, and I imagine it would work quite well in Ohio, where we can build a large enough reservoir. And we're talking about something between 3 and 10 acres in size to be able to irrigate 100, 150 acres. What we're doing is filling that during the wet season out of a drainage ditch in the lower right-hand corner. And then a lot of these are going to have a small well running continuously. Some cases we're doing those with solar wells to keep the costs down, and they keep the pond topped off. So it's ready for use and for both the irrigation purposes and the recycling of the water. Some cases we're pulling right out of drain tiles. That's very popular in the thumb of Michigan. The 6 or 7 that I know of are all set up so that they go into a holding container, a couple 1,000-gallon holding container, and then they have a pump that cycles on and off to lift that water into their retention reservoirs. It's not a cheap way. These are more in the $100,000 range, where typically the wells that I see for irrigation purposes are more in the $30,000 range. As we're irrigating, we don't actually pump water into the crop. We pump water onto the soil. We hope it goes into the soil, and we hope our soil can hold on to it and keep it in the root zone for the plant to take up. So we're actually feeding the soil. Unfortunately, my soil's like a piggy bank, but if I overfill the piggy bank, water and nutrients that I have potentially go out the bottom. So we want to avoid that. A couple different ways of working with that, but the lower your roots go into the soil, the more likely you're going to be able to recover water. So what we have here is a few soils from Ohio and the most common soils in Indiana and Michigan that are irrigated. Notice there's, when we get to 36 inches of depth, Ashtamo, the most common irrigated in the irrigated zone, holds about 5 inches of water. If we said we're using 1/4 of an inch a day, that means that's 20 days from an absolute full profile. In other words, if I got big rains on the 4th of July and filled my profile up and then got no rain for the rest of July, about the 20th, my soil, or I guess 24th, my soil 20 days later would run out of water. If you look at some of the silt loams that you have there in Ohio, you're getting about 3 or 4 extra days of capacity. Now remember, this does not include any saturated zones. So you may have water actually free between the particles. When we think about holding capacity, it's the particle of soil and the film of water around each of those particles of soil. But if we have saturated zones, we may be able to drink right off the bottom, and then this is, becomes a mute thing. You can look these up in your soil surveys. It's going to be under the physical properties, and they're going to have the amount of water that your soil can hold in inches per inch of soil depth. Here's a nice little chart of irrigation scheduling, but basically what we get here, the important thing is we get too little water in the soil, plant starts to wilt, we reduce yield. If we get too much water in the soil, we leach out or refill the aquifer underneath. What we're trying to do is make sure that we're making full use of any water that we're pumping. That said, there's a few times that we want to irrigate without concern of how much water the plants are actually using. Some of the greatest impacts of water that we have from overhead irrigation is the incorporation of fertilizers and herbicides to get them to work. Nothing's worse than to put a full package of herbicides on, not get them integrated into the crop and used into the soil, and end up having poor weed control. So actually a timely irrigation to incorporate herbicides, incorporate nitrogen to reduce volatilizations, all excellent uses of irrigation water that improves the effectiveness. We're going to talk about a couple types of irrigation equipment. One of the important things that we need to talk about is how fast we put the water on. When you have sediments that are tight like you do in Ohio, the water does not want to infiltrate very quickly, so we need to put the water on pretty slow. The diagrams there, if you think of the on the graph, the first one that's highest up there, that's going to be like a drop nozzle off of a pivot, and it may put on 1 inch of water in something in the 10-12 minute range. If I have that spray out a long ways and the pivot's moving across the field, much like your sprayer does, the faster you move, the less you put on. If I have it spraying over a larger area, I may put that same 1 inch of water on in as much time as 80 minutes. So it's important to make the right discussion or application sprinkler decisions. A couple ways of getting this all done as far as overhead equipment. Linear moves are not very common, but they are very in their position, or where they really fit well is where we have a field that's 2.5 times or 3 times longer than it is in width and is flat. Okay, so it actually crawls across the field. Each sprinkler is putting on the same amount of water, and it's going to require that hose to be moved about every 6-8 hours is what they time them at. So there's a little bit of extra work. This is the research tool. Most of these that I know of in the states that I work in are on research farms because it allows us to do multiple applications. Probably the next system as far as acreage covered is big gun travelers. We see big gun travelers come in two varieties, soft and hard hoses. The hard hose is going to be like a big straw rolled up. Soft hoses are more like your fire engine hoses that fold flat. Either way, they've been designed to cover about 10 acres. That's a chunk 300 foot wide. So we're going to go through the middle of it. The gun is going to spray water 150 feet each side of the irrigation lane where the machine is being pulled through. And it's going to cover about 1,320 feet. In the case of the soft hose traveler, they're a little more efficient because you're using about 630 feet of hose, and you're going down and back, and the water supply, as in the diagram in the upper right, comes down the center of the field. And then there's a cable, 1,300 feet of cable that's used to pull across the field. Hard hose travelers have no cable. They're using the actual hose to pull the sprinkler across the field. And you have 1,300 feet of hose to do that job. Be careful. A lot of this is sold as used equipment. In a lot of cases, the hoses are more expensive, the replacement hoses, than the used equipment themselves. There's a reason why this stuff comes out of the garage in the dry years and gets sold. People that are unaware of the cost of the high energy input to do irrigation this way, an extreme amount of labor that's required to do that, are often motivated to use traveler irrigation. But it is a way of getting started, and it's extremely flexible about field size and where we can be established. Center pivot irrigation is the king. 85% of the irrigated ground in Indiana and Michigan is center pivot irrigated. It's based on acreage. 160 acre units tends to be the low cost point. Bigger equipment, bigger pipe sizes required when we go over that, which sort of cuts down on that geometry advantage that we have on larger sizes. It is very dependent. It's much more expensive to do 40 acres than to do 160 acres because all you do is double the equipment size between 40 and 160, but you get 4 times more land covered. That said, a lot of our center pivots have an end gun on them. It may have a booster to keep the pressure low across the whole machine and then booster the pressure up when we need it. This is a large gun that may use between 100 and 170 gallons per minute. And it picks up that outer edge. Typically in a 160 acre field, about half the time this end gun will be on, and it will pick up a portion of the corners. It will not pick up all the corners. Typically our 160 acre field will have 142 irrigated acres in it. There are places in Indiana and Michigan we're now using cornering arms. This is an accordion fold system or a leg that swings back and trails. And then when you come to the corner or the area you want to get bigger, it is deployed and expands out. They tend to be expensive, but helps fill fields where it's important to have total coverage. And then the last thing on center pivots, it is possible to tow them. Be careful when you're pricing things. I see ads like the one on the bottom where we talk about 4 different tows, and it's hard to get over more than 2 circles in a year. Remember, you need to have the total pump capacity for all that area that's there. Some of you are going to ask, well, how much does it cost? We did these back in 2014 is the last time we updated. Remember in 12, we had a big drought. 13 and 14, irrigation equipment went up dramatically in prices. Since then, we've had actually a slight reduction in prices up till this winter. Just here in January, we've seen some across the board increases in prices in the major 4 or 5, actually at least 4 that I know about have all raised prices here since January 1. Hoping that the ag market's going to be better than it is. The 160 acre pivot, when you look at the ownership cost of the equipment and the operating cost, it's going to take about $133 per acre to own that equipment and pay the energy bill and the labor bill to apply that irrigation that's there. So a lot of times we're about doubling the rent cost. So if we have $130 rent, $130 irrigation cost equals rented irrigation at that $260 an acre, something in that range. Costs go up from there, smaller pivots being the most expensive, and some of the other systems that are in there have smaller ownership costs, but higher actual operating costs that are there. I guess if you're going to buy something as an insurance policy and only plan on using it every few years, you probably ought to stay towards the low ownership cost and just pay the high energy bills. Some of you are going to say, how much acreage, how much are we going to get in yield increases? I worked for years in sandy ground where we used to talk about doubling yields. We would take people from 125 bushel an acre to 250 bushel an acre. That is not the situation most of you are going to start. We're not going to take 200 bushel ground and go to 400 bushels. In a lot of cases, it's not a lack of water that's keeping our yields down. Take a look at your 5-year rolling average. The last 5 years you've raised that crops. Look at those, look at the highest year and the lowest year. Was the highest year, that is going to be what we would, if that yield was dependent on, we had good rainfall that year, then irrigation is going to help us. If the lowest year in that 5 years was because of drainage issues, that you were late to get harvested or late to get planted, irrigation is not going to help us, and we're just going to have a bigger debt load to have to look at there. And then last but not least, corn is about a 2-to-1 increase as far as irrigated yields over soybeans. Soybeans, it's hard to see more than a 10 or 15 bushel per acre increase. It's a good insurance policy for taking out those lowest years, but we don't see that major increase. Because of that, a lot of people working on a corn soybean rotation with commercial crops will end up going to almost continuous corn once they add irrigation. There's an online couple nice tools available to talk about investment costs, taxation, depreciation, and how profitable the situation will be. I see a number of producers, they get these models built and they work through them. We looked in the last year in 2014, we looked at investments, and remember prices had fallen quite a bit into 2014 there. And we could not make money when we were looking at $3 corn and $9 beans. And if we were at that actual years, we were looking at even lower bean costs. So it was just no way to make money when things were that cheap. We're only increasing debt load at that point. If we looked at $3.50 in corn and $10 beans, and if you remember right, last summer, that's sort of where we were thinking things would end up. There are profits available at the cheapest or lowest in cost investments. The biggest fields with the least amount of well cost or water supply cost, lowest energy, those types of things paid off well. And when we get above $4 corn and $10 beans, and we keep the cost in line, you know, something under $1,300 per acre investment per actual irrigated acre, we could make money at those levels that are there. Last but not least, I know I was supposed to talk about overhead irrigation, but if I was in Ohio and I looked at the costs that were there, I may be more interested in, especially if I had a limited water supply, I may be more interested in looking at subsurface drip irrigation. This is the idea of using a drip tube planted at 15 to 18 inches under the soil surface. You can see the main line there in the trench, and seeping the water through. The one here is on 45-inch spacings, but if we have heavier soils, we may go to 60-inch spacings. The places, there's a nice bulletin at UNL, University of Nebraska, Lincoln, that talks about this and evaluates where it's at. Or I would look at trickle irrigation, and especially if I'm looking at vegetable crops, and look at disposable trickle line. This has worked out well for like the tomato industry, the red gold growers, and it's a much more labor intensive, but these are good ways to get started irrigating and protect a little bit of your crop from those times. I bet I'm out of time. Do you want to take questions now or later, or my information's up there? I am more than happy to talk to people that are looking at investing in irrigation and help give a little bit more details. The office number isn't very usable right now. Catch me on the cell phone or send me an email. Emails work great.
What is a tile spacing recommended for subsurface irrigation in clay soils? And is there any research comparing controlled drainage versus subsurface irrigation? It looks like Larry's going to answer this one. Larry, you're unmuted, so go for it.
Okay. Generally, if you're using whatever drain spacing you use on that soil for subsurface drainage, what we have seen in practice over time is you would have to go in and either split, put one line in between the two existing laterals or put two in. So, you know, you're looking at tighter spacing to be able to get good sub irrigation and get water uniformly across between the two drains. So 1/2 to 1/3 of what your current drain spacing is for subsurface drainage. I've got a fact sheet. Dusty, if you will email me, I will send you a fact sheet that's got a little more information in there about sub irrigation. As far as I know, there may be 1 or 2 short-term studies looked at controlled drainage versus subsurface irrigation. I believe Bud Belcher in Michigan many years ago did 1 year looking at these, and I'm not sure if that study was ever published, but give me a little time and I'll see what I can find. There may be a study in Jane Frankenberger's project going on where somebody's looking at controlled drainage and sub irrigation with the same plot, and there may be something in North Carolina State. I'll try to look into that for you. But shoot me an email, Dusty, and I will see what I can get to you.
Thanks. Just a reminder, we also will be sending out a post-webinar email with a few of those fact sheets, so keep an eye out for that. I do have one question, not in the chat, not in the Q&A, that kind of relates back to water quality, potentially for Eileen and Larry again. How do we balance tile spacing benefits and water quality impacts? Do narrow tile spacing equate to more nutrient loss and discharge volume?
Hey, Eileen, you want to go ahead and then I'll follow?
Yeah, I didn't include any of that information today, but definitely our work has shown that the closer you bring tiles together, you put tiles closer together to get rid of more water faster, which means you also have more nitrate being lost from the land. So we want to try to not just put tiles closer and closer and closer together if it's not necessary. If we feel like it is necessary for the purposes of managing the water, then my plea with people is to also intensify some other aspect of managing their nitrogen, which might mean cover crops, for example, so that cover crops can be taking up some of that nitrate during the off season when we would be losing most of it. But that's an excellent question. We don't want to just intensify drainage beyond what is necessary for our crop production needs. But if we're intensifying it, we're going to lead to more nitrate loss. And therefore we need to do even more related to managing nitrogen. And that's not just putting on the right fertilizer rate, right? It means we have a leaky system. And so it means something like cover crops, or it could mean the controlled drainage that reduces the amount of drain flow that we get during the off season.
You're right on, Eileen. Several years ago, before the current Purdue project that's across the Midwest, a bunch of our Midwest states got into a CIG project, Conservation Innovation Grant. And we looked at controlled drainage or drainage water management, and we were looking at implementation of that practice to reduce nitrate loss or nitrate load. And what we found was that you don't really reduce the concentration that much, but you are reducing the pounds of nitrate and nitrogen that go out the drain. Now, Dr. Fauci has studies that showed a very nice impact, going up to 50% reduction in load. And if we found that if we reduce the total outflow on an annual basis by, say, 25% or 50%, we might also see a reduction of 25% or up to 50% in the load of the pounds of nitrate and nitrogen being discharged. Now, Dr. Fauci has some good study, good work that he did in Northwest Ohio looking at sub-irrigation. And I was going to show some of these slides, but I didn't, and I can add those into an email, whoever's interested. We end up having to illustrate that. I just didn't put it into my presentation.
Thank you. We are just quickly going to reshare that CCA code before too many of you log off. The first one you might have been having trouble with. Sorry, Larry, you can go for it.
I've read a little bit on the CCA, the 360 rain, and that is a system of managing the entire field. And if you're irrigating, but I don't know that much about it, but it seems like that's a systems approach that I've seen in some of the farm magazines. And that may be what that 360 rain is about.
Awesome. Well, I'm glad you could give your input on that as well. It seems like we are out of questions and also out of time. If any other panelists have anything else they want to contribute before we sign off, we can keep it running, keep the CCA up for a few more minutes. But if anyone has to leave, feel free to drop off. But Eileen, you can.
Well, there was one question. I don't know where it disappeared to, but the comment about the USDA NRCS principles of building soil health and so on, and that sometimes some folks will say, if you do all that, then you don't need drainage. I strongly disagree with that for some of the reasons that I said in my talk, that if you have if you're trying to do conservation practices, but you have a naturally poorly drained soil, right? So a soil that has a high water table naturally, all of those practices that we do to improve the soil will help water get into the soil and will help it permeate through the soil. But a naturally high water table is not resolved by those practices. So I don't agree that you don't need tile drainage if it's a naturally poorly drained soil. Now, if it's a sloping soil that has had some other issues because the soil properties have kind of deteriorated, then yes, those practices may be sufficient by themselves. But if you have a flat soil with a high water table, improving infiltration and rooting and all that is not going to deal with that high water table. And in fact, by putting in drains, you then allow all those other conservation practices to work better.
I second that, Eileen.
Good.
So Bridget supplied us with the link to 360 rain, and 360 rain is one of the newer, the question about 360 rain, it's one of the newer autonomous travelers, runs on a 3-inch hose. drops water supposedly on a wide drop between the rows so that we're eliminating the foliar disease potential and some of the evaporation from the surface. I look at these things very closely, look at how successful it's been, and then look at the environment. Is the environment where it's been successful our environment? We don't lose a lot of water to evaporation, about 1/10 of an inch of water per application to evaporation. So when I see claims on the site there about using 40% less water than center pivots. And then the second issue is if we're dropping water from a boom, like a sprayer, like we do nitrogen for side dressing, are we dropping it so fast that we're going to have water running down the rows? That's the other issue that's there. But I'm not saying new things are bad. Find somebody that's used it, gain knowledge from him, and try those things, with a little bit of caution. Be glad to talk to whoever had the question, though.
Speaking of caution, back to that question regarding the 3-inch tubing versus the 4-inch tubing. Dr. Brown, you had kind of shared in some comments about installation, maybe differences between 3-inch tubing and 4-inch tubing. I guess as we evaluate options, what kind of remarks might have about installing 3-inch tubing versus 4-inch corrugated plastic tubing?
Okay, that's then I was going to jump in on that, Bruce. My recommendation is that if you're using a standard drainage plow, full-size drainage plow, and you have very good grade control capability, you're probably going to be, and you have experience, you can lay 3-inch just about as well as you can lay 4-inch, and it'll be fine in general. If you are using a pull-behind plow, or your grade control system is not that good, or you've got problems with it, you can very easily install in the 3-inch, would have some ups and downs, some highs and lows in it. And we've seen that just out in the field from time to time. So with a 4-inch, and you get off grade by say 10%, you take the same 10% and look at the 3-inch, and you may end up having a block tile over time with a low place or a high place with the 3-inch sooner than you would the 4-inch. So installation quality is very, very important. And I know there's a lot of companies that are recommending 2-inch across the Midwest, and in the 3-inch, I've heard of a tile manufacturer or salesman say that the 3-inch can carry the same as a 4-inch, but it depends on the grade as well. So I would just be very careful if you're going to install it or have an installer, make sure they've got a good installation system that they can work with, and get it done on grade. Thanks, Bruce.
Great. Thank you, Dr. Brown, for that comment. And with that, unless there's anything else that someone wants to add, I think we will go ahead and wrap up for today. We appreciate all the panelists, especially staying on these extra 10 minutes or so. Appreciate everybody's expertise and willingness to participate, and as well as all the attendees. Thank you for joining from wherever you are. This is a good opportunity to bring folks together from tri-state area. So thank you, everybody. We appreciate your time and look forward to seeing you again in the future. So everybody have a good day. Thank you.